All magnetic fields are due to the motion of electric charges. This includes the field created by an electromagnet, as well as the field created by a bar magnet. In the electromagnet case, it's easy to identify the motion of charges as the current flowing through the wires of the electromagnet. However, in the case of the bar magnet, where are the currents? What gives rise to magnetism in materials? It turns out the current is due to the motion of the electrons within the atoms of the material itself. The magnetism produced by electrons within an atom can arise from two different motions. First, each electron orbiting the nucleus behaves like an atomic-sized loop of current that generates a small magnetic field, similar to the field created by a current loop that we have studied earlier. Second, each electron possesses the physical property of spin that also gives rise to a magnetic field. The net magnetic field created by the electrons within an atom is due to the combined fields created by their orbital and spin motions. In most substances, the magnetism produced at the atomic level tends to cancel out, with the result that the substance is a non-magnetic material overall. However, there are some materials, known as ferromagnetic materials, in which the cancellation does not occur for groups of approximately 10 to the 16th to 10 to the 19th neighboring atoms, because they have electron spins that are naturally aligned parallel to each other. This alignment results from a special type of quantum mechanical interaction between the spins. Quantum mechanics is a branch of physics that describes the subatomic world, and we will discuss this topic briefly in Chapter 29. The result of the interaction is a small but highly magnetized region of about 0.01 to 0.1 millimeters in size, depending on the nature of the material. This region is called a magnetic domain. Each domain behaves as a small magnet with its own north and south poles. Common ferromagnetic materials are iron, nickel, cobalt, chromium dioxide, and alnico, which is an alloy of aluminum, nickel, and cobalt. Often, magnetic domains in ferromagnetic materials are arranged randomly, as the figure illustrates for a piece of iron. In such a situation, the magnetic fields of the domains cancel each other, so the iron displays little, if any, overall magnetism. However, an unmagnetized piece of iron can be magnetized by placing it in an external magnetic field, provided by a permanent magnet or an electromagnet. The external magnetic field penetrates the unmagnetized iron and induces or brings about a state of magnetism in the iron by causing two effects. First, those domains whose magnetism is parallel or nearly parallel to the external magnetic field grow in size at the expense of the other domains that are not so oriented. Second, the magnetic alignment of some domains may rotate and become more oriented in the direction of the external field. The resulting preferred alignment of the domains gives the iron an overall magnetism, so the iron behaves like a magnet with an associated north and south pole. In some types of ferromagnetic materials, the domains remain mostly aligned when the external magnetic field is removed, and the material thus becomes permanently magnetized. The magnetism induced in a ferromagnetic material can be surprisingly large, even in the presence of a weak external field. For instance, it is not unusual for the induced magnetic field to be 100 to 1,000 times stronger than the external field that causes the alignment. For this reason, high-field electromagnets are constructed by wrapping the current-carrying coil around a solid core made from iron or other ferromagnetic material. Induced magnetism explains why a permanent magnet sticks to a refrigerator door, and why an electromagnet can pick up scrap iron at a junkyard. Notice in the figure that there is a north pole induced at the end of the iron that is closest to the south pole of the permanent magnet. The net result is that the two opposite poles give rise to an attraction between the iron and the permanent magnet. Conversely, the north pole of the permanent magnet would also attract the piece of iron by inducing a south pole in the nearest side of the iron. In non-ferromagnetic materials, such as aluminum and copper, the formation of magnetic domains does not occur, so magnetism cannot be induced in these substances. Consequently, magnets do not stick to aluminum cans or to copper tubing.